ALIS and Dataland podcast is a trip down the rabbit hole into autonomous learning investment strategies. Michael Weinberg is the Chief Investment Officer of Move37. All opinions expressed by Michael and podcast guests are solely their own opinions and do not reflect the opinion of any firm. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. Clients of Move37 may maintain positions in strategies and securities discussed in this podcast.
Welcome to our podcast series. We'll be exploring new developments in autonomous learning investment strategies, whose acronym is ALIS. We'll also be exploring artificial intelligence, data, and blockchain. I'm Mike Weinberg, Chief Investment Officer at Move37, as well as Adjunct Professor at Columbia Business School. Hein Hundal will be our guest today. Hein is a partner of one of our advisory board members, Rob Wrightson. We believe they are both visionaries in the fields of machine learning, data, and game theory. On that note, Hein, would you be so kind as to share a Reader's Digest version of your background?
Okay. I've never been called a visionary before, so that's quite a compliment. Yeah, I got a degree in engineering, went out and worked in the Navy as both as a meteorologist and as a nuclear engineer, and came back, got a master's degree in computer science and a PhD in mathematics, and then went to work for Raytheon as a satellite engineer. And shortly after that, I met Rob Wrightson, who was my partner. And we got into lots of interesting things like poker, and Core Capital Management was the name of the fund he was running at the time. And then after that, I pretty much bounced between going back to academia, Penn State. I did some teaching there. I also worked on the next generation torpedoes for the U.S. Navy, which is part of the Applied Research Lab at Penn State. And I went back to work for Raytheon for a little while, and I worked for another hedge fund for a little while. And here I am, still working on hedge funds and teaching occasionally.
Nice. All right. We have a view that there's a confluence of four technical factors that are enabling ALIS investing for the first time. So one of those is that machine learning is working after multiple false starts and nuclear winters over the past 7 years, nuclear being apropos to your background.
Yeah.
So along those lines, we believe you may have a similar view on what you refer to as the machine learning revolution, more recently that is. And so maybe you could explain how neural nets became the most commonly used machine learning method for pattern recognition.
Right. So machine learning is pattern recognition, and computers started to get good at pattern recognition in the 90s. After a couple of AI winters where there was a bunch of funding for artificial intelligence, and then it didn't pay off as much because there's so much hype, wasn't paid off, so the funding dried up. And it happened again and again. And then in the 90s, they started using more statistical techniques. And these statistical techniques, like, for example, random forests, worked rather well because we were starting to finally get the computational power. And some of the simple techniques, like k-nearest neighbor is a machine learning technique, it started to work because we started getting, instead of thousands of images, we get millions of images. And the computational power that we had available to work on our AI algorithms increased and increased. Neural nets did not seem to be paying off all that well. They were kind of okay. And then a big revolution happened in about 2006. Gregory Hinton developed a technique to take these neural nets that were really difficult to train, and he found a way to train deep neural nets. And he made an announcement at NIPS where he did some digit classification and deep neural nets that were like 6 and 7 layers deep, trained rather quickly. And this was a huge step forward, and it kind of revolutionized the field. And all the different types of pattern recognition, handwriting recognition, facial recognition, speech recognition, they all had their own separate techniques, their own little support vector machine was one method that was used over here. A mixture of Gaussians was another method used in another field. And neural nets started to take over every single one of these fields. And Hinton came out again in about 2012 and came out with another technique called dropout. Now, I say Hinton, but maybe I should say University of Toronto, because he had a big team there that were working on these things. And dropout prevented overtraining of the neural nets. It used to be you would train the neural net for a while, it would get better and better, and then it would start to get worse after you send in more training examples. With dropout, it introduced noise into the training process, and for some reason that really isn't understood very well, but his dropout paper is quite good. Maybe that's why. It allowed you to train and throw thousands of computers at one problem, and it would just get better and better and better. And now, come about 2013, 2014, using these dropout techniques, neural nets are starting to beat humans on tasks that they just were not very good at in 2005. So, for example, recognizing images or recognize a speaker, they're doing better than human beings. And just kind of amazing.
Why, you mentioned that, which we didn't quite understand. If we're creating these neural nets, why or how don't we understand? Shouldn't we understand?
Yeah. Well, the way that neural nets work is you expose the neural net, which is kind of an imitation of the brain. There's neurons and there's connections between the neurons. You expose it to many, many different examples of what you want to recognize. So if you want to recognize pictures of dogs and cats, you show it lots of pictures of dogs and cats. You label the pictures with dogs as being dog, and the ones with cats being cat. And every time it sees a new example, it tweaks the connections between these neurons. But there's no engineer that's saying, well, I think that this part of the neural net ought to be recognizing the floppy ears of a dog. Or this part of the neural net should be recognizing that cats have 4 legs and airplanes don't. There's no engineer hand creating features to look at. It's all learning it on its own. And we find that we don't really understand the exact function of the neurons or why they're combined in the way that they are. And what they do try is they say, here's a neuron that's inside the neural net, and say, what does this neuron most stimulated by? And in the lower layers, it might be the edge. It might detect edges, vertical edges, horizontal edges, or curves, or something like that. In the middle, it might detect like an eye, or a tail, or a fluffy ear, or something like that. And only the top layers is it starting to recognize cats and things like that. But that's almost the extent of our understanding of what's going on in these neural nets. And we don't have a whole lot of theory as to why these are working out very well.
Interesting. So shifting gears a bit, though we are averse to confrontation, we'd like to ask you non-confrontationally to describe a generative adversarial network, which, like everything else in machine learning, has an acronym, which is GAN. How do we evolve from neural nets to GAN?
Well, okay, so back to our story. I guess about 2012 or so, dropout was kicking in. The neural nets were getting really, really good. And there was a man, Segdi, who worked for Google. And he had a team that worked for Google. And they noticed that they could take a picture of a cat that was recognized as a cat and just change it a little bit. Changed many pixels, but changed the pixels just a little bit. And the neural net says it's not a cat. But the picture looks almost exactly the same as it did before. They found that this happened if they had to really analyze the neural net to do this. But they could get a picture that was correctly classified, and just by changing a few things, well, several pixels in subtle ways, they could change the classification from being a correct classification of a plane to not a plane, or to a cat, or something like that. And so this was a crazy thing. And one of the co-authors for the paper, Ian Goodfellow, I think it was, he came up with this idea, well, what if we have another neural net, that's just trying to tweak the pictures to make them look like something else. It's sort of a competitive. It creates images that look sort of like a cat but aren't a cat. And then have another neural net that learns to distinguish between real images of cats and generated images of cats. And this competition really massively improved the field and created these generative models. The generative models actually create pictures of cats rather than classifying a picture as being a cat or a dog. You say, give me a picture of a cat. It gives you a picture of a cat. In fact, you can even say, give me a picture of an orange cat. And it gives you a picture of an orange cat. Or give me a picture of a celebrity. And it makes something that looks like a celebrity. It's not any known celebrity, but it looks like a very pretty looking or a handsome man. And at least initially, it even fools humans in a short term. Now, when a human looks closely at it, goes, no, that ear looks funny. That's not a real person. But the generative networks have been really cool in creating new things. And this classifier that was getting fooled by just small changes now becomes much more robust because it's got another thing that's trying to fool it all the time. And it's learning not to be fooled.
Are there broader implications in society from GANs or?
Yeah, I think so. I think you can manufacture images of things that have never occurred, or maybe you might be able to create films from nothing. Not real characters, but generated characters like that. I don't think we're at that level yet. Right now, humans can still distinguish between these computer-generated concepts and computer-generated images and an actual image. But it may get better. The important things about GANs is it's creating this generative model, and it's also improving neural networks even more than the dropout was doing.
Well, to your point, I spoke at the Frick a few weeks ago with a scientist from Google, and they're experimenting with neural nets creating text. So Wikipedia entries, for example, and other fiction. Yeah. So I guess to your point, if you have GANs creating images and you have neural nets creating text, you combine them, theoretically one could have synthetic art, I guess, or literature or whatever the case may be.
Exactly.
Or film. Right. Interesting. So shifting gears again, how does a practitioner risk getting lost in the proverbial forest or having a neural net create a mirage? Yeah. So obviously I'm referring to overfitting, but...
Right. Yeah. So this happened to us actually in the Navy also, is that we would try to train sonar in order to recognize certain things underwater. Maybe recognize... At the Applied Research Lab, they were actually tracking whales, for example. And... if you train the sonar just in one particular bay or something like that, then it only learns to recognize the things in that bay. And when you take it outside of that bay, it gets very confused about what's going on. And this happens all the time in neural nets, is that we don't have enough data to feed it to recognize all situations. And we get this confidence that we think we know what's going on, and we apply it to a situation where it doesn't actually know what's going on, but it doesn't tell us. Often it doesn't tell us. And so we can become overconfident about what it's doing. And it can give us false information because of that.
But that's a great segue to my next question, which is DeepMind's Go computer turns out to be quite adept at chess as well, despite having been trained and built on Go. Does that imply that we're moving down the path of, or already down the path of general intelligence?
It was a huge step. So you're talking about AlphaZero.
Yes.
So AlphaZero is amazing because it was trained only by playing against itself. And so prior to that, all chess computers and all of the Go computers were trained mainly by looking at past games by human experts and almost being guided by humans as to what's going to happen. AlphaZero trained itself, and it used this technique called reinforcement learning together with neural nets, which really hadn't been combined very often before. There was some work back in the later 90s on it, but it kind of died, and it was brought back by Google DeepMind. And this combination of neural nets and reinforcement learning allowed it to play against itself, and it would just get better and better and better. Sort of this, like the GANs, they had kind of an adversarial relationship going. And for chess, they took thousands of computers, had them play against each other for 5 hours, and the resulting computer was stronger than any other computer program ever written for chess. I'm exaggerating a little bit. There's some caveats in there, but it's just kind of amazing. That was accomplished in 5 hours. Now, they did think that after 5 hours that it wasn't improving that much after that. I don't know if it reached perfection or what. But when it played against our top chess computers, which we thought were getting pretty close to perfection, found that it made them look silly. The chess computers that we had trained, us humans had programmed, were very concerned about keeping pieces and the value of the pieces, whereas this computer that had trained itself managed to block a piece so that it couldn't get out. A bishop would be trapped in a corner, so it was useless. So maybe Black's bishop was trapped in the queen's corner, queen side, and maybe Black had more stronger material advantage. So our human trained computers said, we're winning, we're winning, we're winning. But when grandmasters looked at it, they go, well, hey, that bishop's never going to get out of there. It might as well not even be there. And it outplayed our best computers, chess computers. It's really kind of amazing.
Well, that reminds me of the 37th move in one of the infamous Lee Settle matches in Go, where the piece was placed somewhere and Lee Settle, the critics, everyone in the world thought it was a mistake. The computer was broken. It didn't understand it. And actually it was a move that had, to my knowledge, never been seen in thousands of years of Go playing. And one might actually, and in my view, it was actually almost creative. I'd be curious to hear your thoughts on that. And is machine learning, our neural nets, are they actually creative? Are they being creative? Or?
Yeah, I would say so. It's finding cool new ways of doing things. In Go, the computer is invading on the 3-3 point, which is in the corner, and it was thought to be way too aggressive prior to the AlphaGo computers doing it. The move that you're talking about is interesting because it came about as sort of a conflict. That AlphaGo was not, that one was trained off of human games. Right. That was earlier one. And in that one, it had one neural network for saying, what are the most likely human moves? Because we want to look at those. And another one that kind of figures out, well, okay, so given those moves, what's the best one? And I'll look at a few others also. The move that it chose, that one that was move 37, was said only 1 in every 10. It only had a 1 in 10,000 chance of being a human move. It was thought this was totally an inhuman move. So initially, it didn't give it that much weight, but the network that decided to evaluate the moves looked at it and said, no, I disagree with the humans on this one. I'm going to do this move. And Michael Redman, the 9th Dan professional Go player, I think he's the strongest European one of the strongest Go players that speaks English anyway, was reviewing the game, and he put it up there, and he just looked at it and goes, is that right? Is that right?
Exactly.
Yeah, it was kind of almost a revolutionary move. And we're seeing things in chess, like I mentioned, that are going beyond the state of the art. And it's neural nets. By the way, the chess computers did not use neural nets at all until AlphaGo came out. The AlphaZero chess computer.
Right. My understanding is that chess computers historically were more traditional programming rather than true machine learning. Is that fair?
Yeah. All the best ones used something called alpha beta search, where it basically looked like maybe as many as 10 moves by each side ahead.
Right.
And just looked at almost all the possibilities and said what could go wrong and what could go right. Whereas the AlphaZero tended to play to the end of the game and it would repeat or look at situations. In a sense, it just played out the end of the rest of the game many, many times, and then used neural nets, which were not used before, to evaluate the positions. And before, everything was hand-tuned by humans that were studying for a long time. It helped a lot if they were great chess masters and that sort of thing. Whereas AlphaZero was just playing against itself, didn't get human input.
So the contrast is it was man or woman plus machine, and now it's man or woman guiding machine but much more of the machine.
Yeah, it's much more of the machine. I mean, they set up the neural net, so they set up a different neural net for chess than they used for Go, and that requires some certain amount of skill. And they set up the neural net to take advantage of certain things in chess, and so it knew that the squares were connected to each other, and so there was some skill there. But it didn't say, well, this is. I think you really look carefully at the two bishop advantage, or look carefully at a pawn that can't be attacked by other pawns. It's been passed. Those were the kind of characteristics that we thought were very important. We didn't tell it any of that. I said, well, we set up this neural network, go learn.
And it did.
5 hours later, it was better than anything we'd ever created.
Fascinating. Shifting gears again. So we've been working on a research paper with the World Economic Forum, and one of our views that we've expressed with them is that AI will be massively disruptive to employment. It'll be non-discriminatory and traverse all colors of employment, ranging from blue to white, from portfolio managers to autonomous vehicles or drivers. What are your views on that?
Oh, I think that we will continue to see the revolution proceed. X-ray interpretation done by radiologists with years and years of training. They're not that much better than the best AI techniques applied to the same images. And it turns out it's not that expensive to have a computer around to do your diagnoses, rather than to have a doctor who spent 8-10 years perfecting his craft. It's much cheaper to have that computer. And lawyers, even in law, we're finding that computers are getting very good at searching through thousands and thousands of documents for what's relevant to our case now. And the junior lawyers are just not as important as they used to be. Same thing happened in engineering, just from computers. Right now, what used to take 20 engineers back in the 1960s is taking one fairly smart engineer with a good computer. And AI is changing things. And, of course, the autonomous vehicles, what's going to happen with the trucking industry? What percentage of the United States are truckers? It's one of the most popular jobs in the entire United States. Very disruptive.
Agree. Anything we haven't asked you but should have for this brief podcast on the evolution, or in your words, the revolution of machine learning?
No, I think that we've covered most of the bases here. And I think that if you wanted to go further, that maybe you ought to take a course by like Andrew Ng, who has a very nice course out of Stanford, for example. But I think, we've covered the scary parts.
Well, we haven't discussed Elon Musk and his views, but we'll save that for a future podcast. Look, I'd like to thank you for your time. That was fabulous. We look forward to your joining us on future podcasts, where we'll delve more deeply into some of these subjects and other ones that we haven't had time to discuss today.
Well, thank you very much, too.
Pleasure.
Thank you for listening to Alice in Dataland. For show notes and more information on Alice and Move 37, please visit our website at www.mov37.com.